Hi and welcome to this lesson. We are looking at chemical energy changes and specifically reaction rates or the rate of reaction. Now, whenever we talk about rate, if we talk about the rate of a reaction or the rate of something, we are talking about a change over time. So a change over time. And the change, well, it can also be a change in time. The change that we're going to look at when we refer to that rate of a reaction is the change in the reaction. The change in the reaction. Now, what do we mean by that? Well, what is changing when we have a reaction? In a reaction, we have reactants forming products. Product C and D. And the rate of reaction would refer to rate of reaction would refer to the change, how quickly are the products, the reactants used, or products formed. That's the question. How quickly are the reactants used and the products formed? Well, the way we would do that is we would look at either one or all of the reactants, and we will measure the change in the quantity of reactants. Now the quantity, so we will look at change in quantity. In quantity divided by how long did it take for that change to occur. Now, quantity can either be in mole, which is a standard unit that we might use, or it can be in grams. So that the unit for a rate of reaction, the unit could be mole per, let's take away the E, per second, or grams per second. Now we're not going to be too concerned with the actual value that we're going to look at, like we really want to know, what is the value of a reaction's rate of change, but we are more concerned with how can we increase the rate of change. How can we make the reaction go quicker, or what is influencing the reaction to go so slow? Now those are the more important factors here, but it is still important that we know how to calculate it. Now, one way in which we will then do it is if we can have the change in the amount of reactants used. Now it will be different for different compounds. So if I would use one compound and I just look at the amount of reactants that are used up by this compound, and I calculate it, and I measure what the rate of change is for this compound, it would be different. And the same as if I were to take a total, the rate of change, if I take both and see what is the total moles used, or rather the total grams used for both. And the same goes for producing. Because as soon as we balance this equation, the balanced equation, let's just give an example, might look something like this. It's obviously not balanced here, but a balanced equation might just show a different amount of or ratio of a certain product used. So for one gram used here, or not necessarily for 1 moles used here, we might use 2 moles there. So the moment I measure in moles, then 2 moles of this is produced and 3 moles of that one is produced. So obviously over time, the one with a higher production of moles will have a higher rate of change, because the change goes the change is more per mole. Okay, so that being said, one other way that we can go and calculate it, so in one way we'll actually go and measure the amounts of moles or the amounts of grams that is changing. How many moles are there in my container at the beginning of my reaction, and after a few seconds how many moles are there now, and then we use this calculation. So it would be something like the quantity in the future minus the quantity initial over the change in time. And quantity can therefore be either in future minus in initial, in other words moles, over a change in time, or it can be mass in the future minus mass initial divided by a change in time. And if I have this one, I can always just calculate that one. It doesn't matter, using my formula, N is equal to M mass over molar mass. But again, this is a minor aspect of the whole process. What we are more concerned about is what are the factors affecting the rate of change, and how can I therefore increase it. But there is another way that or another important matter that we need to consider. If I were to take a graph and I were to measure on the one side my the amount of moles or the amount of grams on my vertical axis. On my horizontal axis, I have the amount of or I have the time. Okay, notice in maths, this would be my y-axis, this would be my y-axis, and that would be my x-axis. Now if I were to take the change in mole or the change in grams, I would actually be talking about the change in my y coordinate. If I were to take this and divide it by the change in time, I would actually be talking about the change of my horizontal, my x, my change in my x. Now this, I'm sure you know, is gradient. In other words, it's the steepness of a certain, the steepness between 2 points. So if I were to look at a certain product, that product will start with a certain amount of, we'll have a starting amount. In other words, when I start my reaction, I have a certain amount of reactants, but my products will have nothing. Okay, I will have no products. Then as the reaction gets started, okay, it starts very slow, but then all of a sudden it increases, and then at some point it decreases again, and I might be left with some of my reactant. Now the only reason why I might be left with some of my reactant is because my reactant, there might be 2 reactants. Okay, might have been 2 reactants, and now that reactant started here. Or actually, let's start that reactant lower. That reactant might have started here, and as the reaction started occurring, and then eventually I had none left. Okay, at some point I have none of my, so let's call this B, and we'll call that one A. At some point I have none of B left, so reactant A has nothing to react with anymore. Now in this whole process, I have also started with nothing of my product. Let's see, this was the formation, let's say, of O2 plus H2 producing H2O as an example. Now I had nothing to start with, and now as the time goes by, I'm producing quickly, and then it slows down at some point and stops. Now you can see for all of these, it starts to stop at a certain point. Okay, it starts to reduce, to reach the end of the reaction more or less at the same point. So notice now that in working with the gradient, we are talking about the steepness of the graph. The steepness of the graph tells me, of these graphs, tells me how quickly is the reaction occurring. Now you'll notice in the beginning, if I were to look at the steepness, so if there was a little man walking around here, it's not that steep compared to a little guy hanging out here in the middle. Okay, he's having difficulty walking up this hill, okay, in a backwards direction. That means this has a negative slope. So if we go in the reading direction, whenever I'm heading downhill in the reading direction, it means I've got a negative slope. That means my gradient is negative, or my rate of change is negative, which in this case the actual meaning would be is I am reducing. If this is negative, or I'm decreasing. If this is negative, it means the future mole is less than the initial mole, and that means that I am actually losing value. And you can see that I started with a higher value, I end with a lower value. Okay, but now notice, now as the time goes by, the steepness increases, and then at some point it starts sloping down again. So it starts going horizontal again. When it gets to a horizontal position, it means the reaction has completed, and that's why I said at this point it seems like the reaction is slowing down, and maybe at that point it seems to have basically stopped. Now, why does it have this shape? Why is it that it starts slow, goes fast, at some point reaches actually a maximum reaction rate, or a change in the reaction, and the same goes here for the product. It's just the opposite. Okay, I start off a little bit slower, and then I also have more or less at the same time a very high reaction rate here in the middle, and then at some point it slopes down again until the reaction stops and reaches no further reaction. Why does it have that shape? Well, in order to understand that, let me briefly go and look at something we looked at in the previous video. In the previous video, we looked at an energy diagram of the internal energies that exist in the reactants, the internal energy in the reactants, and then we've got the internal energy of the products. Okay, so which is at some different point. It can either be lower or it can be higher, and that depends on whether it's an endothermic or exothermic reaction. But before we get from the reactants to the product, we have these intermediate molecules, and they always have a higher internal energy, and the total of these, the absolute maximum of the internal energies, is called the activated complex. That's what we looked at in the previous video. And in order for this reaction to occur, we need to, so it's a smooth graph reaching the activated complex, and then as the intermediate molecules produce products, we go down there. Okay, now in order to reach this energy level, we need, this is called activation energy. And in order to reach the activated complex, we need to activate energy. So whenever this graph is going upwards, it is adding energy, and if we're heading downwards, it is releasing energy. energy. Now the reason why we need to add energy is because we need to excite the molecules. The molecules or the particles need to collide with one another so that they can exchange electrons. We'll look at the collision theory in the next video. But in order to exchange their electrons, they need to collide with enough energy into one another, with enough force so that you can actually knock that electron right out. And in order to do that, they need enough kinetic energy. So we add energy, giving them kinetic energy until they exchange electrons into intermediate molecules, and then as soon as that happens, they start releasing their energy. And that is why we have this initial slow slope. There are only a few successful collisions in the beginning, but as it starts happening, as we add the energy, at some point the system itself starts releasing energy, and that causes this all of a sudden rundown. Now as it's releasing energy, it's causing more and more particles to interact, but at some point there the amount of reactants available is decreasing to such an extent that, especially here, to such an extent that the probability of a successful collision is low because there are fewer and fewer reactants. Okay, so we get less and less reactants reacting, and therefore there's less and less and less and less products that can form, and eventually there are no more of one of the products. Okay, that, remember, we call that the limiting reagent or reactant. Okay, and that is when we have our reaction coming to a halt. Now that's all I wanted to say really in this video. In the next video we'll actually look at the important aspect, the most important aspect of this topic is how do we we'll look at collision theory and how can we change the rate of reaction. And so I'll see you in that video. Thank you for watching. Goodbye.